Hey guys, welcome to video 75. Today we're going to start talking about transformers, and our ultimate goal is to design and analyze amplifiers using transformer coupling. But today we're just going to look at some basic transformer characteristics and specifications. And on this page we've got some pictures of typical transformers. Over here on the left is an audio output transformer for a single-ended amplifier. Down below, a power transformer. Over here we've got a toroidal power transformer. Beside it, another power transformer, just in a different case style. And some inductors shown here. We've got a solenoidal inductor and another toroidal inductor. And over here on the right are the schematic symbols for inductors with an iron core, ferrite core, and air core. And down below is a transformer, primary on the left, secondary on the right, and we've got some phasing dots shown, which may or may not be shown on a typical schematic, but the interpretation is if I am applying a positive going voltage to this end of the primary winding, we're going to get a positive going voltage on the dotted end of the secondary winding. Or in terms of current, if we have current entering over on this side, we're going to have current leaving over on this side. Now keep in mind that in order to induce a voltage on the secondary, the current entering the primary has to be changing over time, and typically we're going to be driving the transformer with a sinusoidal source. Alright, let's go on over to the next page, and we've got two RL circuits shown here. Now, on the left-hand side, we've got a generic circuit shown basically in what we would call the time domain. That is, we're looking at the response, the current, and the voltage over time for some arbitrary input voltage applied at t equals 0. And in previous videos, we've learned how to analyze circuits like this for different kinds of inputs. In particular, if Vin is a constant DC voltage, we discussed how to analyze this situation in video 10, and if Vin is a sinusoid, say 5 sine 2 pi 1000t, we discussed the analysis of this kind of circuit in videos 20 and 21. But if you've just got some arbitrary input, say 2t squared volts or 5e to the negative 2t volts, well, we haven't discussed how to analyze those situations yet. And we'll get to that in the future when we talk about Laplace transform analysis, and something to look forward to. But again, that's something for another day. Now, if we do have the case of a sinusoidal input, then we can represent this circuit as shown here on the right. This is the frequency or phasor domain representation. And we can look at it either in rectangular form or polar form. As it is here, I've all the circuit parameters shown in polar form, which is really just a shorthand expression for complex exponential form. This just looks scarier, so usually we abbreviate it or simplify it using the polar form representation. Now, we're not going to be using much of this analysis at all in our upcoming studies, which is probably a good thing. But if you're curious, again, go back to videos 20 and 21 to review how these analysis methods are applied. Now, let's go on over to the next page, and I want to take a minute just to talk a little bit about what's going on in the core of an inductor or a transformer. On the left-hand side of the page, we've got a transformer core with a primary and secondary winding attached. And on the primary side, I'm applying a DC voltage, and we're going to use that to establish a primary current, which will induce magnetic flux in the core of the transformer. In the first case, we have no voltage applied, no current, so there's no magnetizing force applied. And we're assuming that all of the magnetic domains in this core are randomly oriented, as I have shown here. Now, that would correspond to the origin of this BH curve over here on the right. This is often referred to as a hysteresis curve, and it's a graph of magnetic flux density in the core, usually given in Teslas, but sometimes in Gauss, as a function of magnetizing force in amp turns per meter. Now, starting at the origin of the graph, if we begin applying an increasing magnetizing force, we're going to get a linearly increasing flux density in the core, and that corresponds to this middle illustration here. We've applied some voltage, we've got some current flowing in the primary, and the induced flux is represented by this red circle oriented clockwise, and we're beginning to have alignment of the magnetic domains in the core along with this flux arrow. Now, as we increase our magnetizing force, eventually we're going to reach a point where all the magnetic domains are aligned. That's point 2 here, and that corresponds to this bottom illustration. If at this point, if we keep increasing the primary current, we're not going to get an increase in flux density because we've already saturated the alignment of all of these domains, and the curve flattens out. Now, if we reverse the polarity of our applied voltage and current, we're going to begin to move back this way, and eventually we'll reach saturation in the opposite direction. That is, all these magnetic domains are aligned the opposite way. And if we keep repeating this process, we'll just keep tracing out this outer envelope of our hysteresis curve. Now, transformer manufacturers have a lot of options for affecting the shape of this curve overall. They can make it stretched out more horizontally or vertically, or they can make it fatter or thinner by varying the chemistry of the core or the geometric configuration. But one thing that's done very often to cause this curve to stretch out more horizontally is that they'll put an air gap in the core, and that's what we're going to talk about next. Here we've got a core with an air gap, and you can see the flux fringes out into space when it hits the air gap. The effect that this has on the hysteresis curve is shown over here. Without an air gap, we have a relatively vertical hysteresis curve. Adding the air gap skews the curve horizontally, and overall it reduces the efficiency of the core, so we need to use a larger, heavier transformer for the same power handling capability as a core without an air gap. So why would we want to use an air gap at all? Well, there are some applications where we're going to have a relatively high DC current flowing through the primary. That would be in Class A single-ended and push-pull amplifiers. And we don't want the core to saturate right off the bat because of this DC current, so the air gap prevents this from happening. And the trade-off is that we have a less efficient core. It has to be larger and heavier to get the same power handling capability. Now, let's talk about some of the basic characteristics of transformers that we're going to be using in circuit analysis and design. And of course, one of the main specifications for a transformer that I'm sure anyone watching this is aware of is the turns ratio, the ratio of number of turns on the primary over the number of turns on the secondary. And from this, we can determine the output voltage for a given input voltage applied to the transformer. Vout equals Vin times Ns over Np. This is the reciprocal of the turns ratio. Now, most of the time, we're going to assume that a transformer is 100% efficient. In reality, the efficiency of most transformers is going to be over 95%, at least if they have an iron or ferrite core. So this is not an unreasonable assumption. And when we make this assumption, the power that's delivered to the transformer from the Vin source is going to equal the power that's delivered to the load. Pout equals Pin. Now let's come on over to our transformer representation over here for a second, and notice I've got a load connected to the secondary, and the input source driving the primary actually is going to effectively drive what's called the reflected load resistance R'(L). R'(L) is equal to the actual load resistance times the turns ratio squared. And it turns out this is a really useful relationship because it allows us to match dissimilar impedances from the secondary to the primary. For example, if we consider the case of a vacuum tube amplifier, we're driving the primary with this tube and it has a plate resistance of, say, somewhere from 1,000 ohms to 30,000 ohms or more, maybe even 100,000 ohms in the case of some pentodes. The load we're going to be driving might be as low as 4 or 8 ohms, typical of a loudspeaker. So we've got a really terrible impedance match between the vacuum tube and the loudspeaker. The transformer allows us to match these impedances, and that's going to give us better power transfer from the primary to the secondary, that is, from the amplifier to the load. Now, you guys know I have a tough time getting through a video without doing some kind of derivation of some sort, and this video is no exception. This time, I'd like to derive the equation for R prime L. It's not really complicated or anything, and it's kind of interesting. So let me try using whiteboard this time, and we're going to start with our assumption that power out equals power in. And from Ohm's law, we know power is V squared over R, so power out is V out squared divided by RL. And the power in is V in squared divided by the resistance we're driving, which we're calling R prime L. Now, what we're going to do next is define V out in terms of V in. That is, we're just going to apply this equation and substitute that into the numerator of this equation. So we've got V out squared is V in times NS over NP squared divided by RL is equal to V in squared over R prime L. We're going to solve this for R prime L, so we'll multiply both sides of the equation by R prime L, and we'll multiply both sides by the reciprocal of this equation on the left, and that gives us R prime L equals V in squared divided by this whole mess, or multiplied by its reciprocal, which is RL divided by V in times NS over NP squared. Now I'm going to write this squared factor out a little bit differently, and that's going to be V in squared over 1 times RL divided by V in squared times NS over NP, the quantity squared. And note that V in squared is going to cancel out, so that leaves us with RL divided by NS over NP squared. And finally, if we take this bottom fraction and invert it and multiply, we get R prime L equals RL times NP over NS squared. And there's our equation for the reflected load resistance. Well, I'm not too sure that whiteboard's an improvement over paint, but either way, here's a nice typeset version of that derivation for reference purposes. And since we're talking about impedance transformation and impedance matching, this is a good time to bring up the topic of maximum power transfer. The maximum power transfer theorem says that in order to transfer the most power possible to a load, we have to match the load resistance to the output resistance of the amplifier or source. And here we see a graph of power transfer to a load versus RL as a function of the output resistance. When RO equals RL, we get maximum power delivered to the load. Now, when we're designing guitar amplifiers and other audio amplifiers in general, what we're mostly interested in is achieving maximum output voltage swing and symmetrical clipping, and that usually doesn't happen when RO equals RL or R prime L. So getting symmetrical clipping and maximum output signal swing takes precedence. But usually they'll be in the same ballpark, so it's not that bad of a trade-off. We care most about maximum power transfer and impedance matching when we're dealing with RF circuits. We're not going to do much of that here, maybe sometime 100 videos down the road, but for now, this is as much as we need to say about maximum power transfer. What I'm going to do next is kind of summarize everything we've covered so far and take a real quick look at a few transformers that are typical of what we might see in guitar amplifier applications. Starting with the power transformer, we're going to take a look at the Hammond 269EX. It's part of this series of transformers, and looking at its specifications, we see it has a VA rating of 43 watts. That means that the product of the high voltage secondary voltage and current plus the product of the heater secondary voltage and current should not exceed 43 watts or the transformer will overheat. It's rated for a 115 volt primary input voltage at 60 hertz, and the secondary is rated at 380 volts center tapped with a maximum current of 71 milliamps for the high voltage secondary. The heater secondary is rated 6.3 volts for a maximum current of 2.5 amps. And we can see over here the high voltage secondary, because it's center tapped, each half is going to supply 190 volts RMS, which totals to 380 volts. Now, this is a very small sample of the number of transformers available from Hammond for use in guitar amplifier applications. If I pull up their website real quick, high voltage plate filament transformers, these are just their general purpose versions that we can design our amplifiers around, and you can see there are quite a few here. They also have a bunch that are designed specifically for replacement purposes for Marshall, Fender, Vox amplifiers, and so on. So there are a lot of power transformers available out there, and we'll talk more about these as we need to when we're designing amplifiers. Let's go on over now and take a look at some single-ended output transformers. Now remember, output transformers that are designed to be used with single-ended Class A amplifiers have to carry a large DC current in the primary, so they have an air gap. That means that typically they're going to be larger and heavier and more expensive than an equivalent output power non-air gap transformer. Now the example we're going to look at here is the Hammond 125A SE, and it's part of this series, and we can see it's the lowest power version here. It's designed to deliver a maximum of 3 watts to a load. It can carry a maximum primary bias current of 25 milliamps, weighs half a pound. And here's the transformer, and here's the schematic symbol for it. And notice that we can match a number of different typical speaker resistances to any number of different primary reflected impedances ranging from 2500 to 10,000 ohms. All we have to do is connect the speaker to the appropriate taps on the secondary. And over here we see an example of a single-ended Class A output stage, the Vox AC4. It uses an EL84 pentode, and if we trace down from the power supply, we see that the amplifier gets its current through the primary of the transformer, and so it's carrying the entire bias current for this tube. And let's finish up by going over and taking a look at a push-pull output transformer. In this case, we're going to look at the Hammond 125B. It's shown here, and here's its schematic symbol. And if we look at its specifications up here, the 125B is rated for a maximum output of 5 watts RMS, and it can handle a bias current of 35 milliamps per side. Now, what does that mean? Well, if we come over here and look at this Fender output stage, if we trace the power supply voltage from VPP over to this node, if we come up to the center tap, note that the current will split between this upper tube and this lower tube, and we can have a total of 35 milliamps per side, so we can carry 70 milliamps out into the power supply or from the power supply into the center tap. Now, this transformer doesn't require an air gap because if we look at the flux that's created by the current flowing into the center tap here, it splits. Half of it goes up, half of it goes down, and this induces flux in opposite directions through the core, so they cancel each other out, and we get a net flux of 0 in the core at the Q point. So that's why we don't need an air gap here, even though we are carrying a fair amount of current in the primary. Now, if we look at the symbol over here for our transformer, we can figure out which lugs we need to connect our speaker to by determining what our speaker impedance is here up on this top line and finding what reflected impedance we need down here. So if we're trying to match an 8 ohm speaker to a 5,000 ohm reflected impedance on the primary, we'd come down, find either 5600 or 4200. We could take our pick here, and we would use either lugs 1 and 5 or 2 and 6 to connect our speaker to. Now, we could do a load line analysis and figure out which is best to use, but generally speaking, we could probably pick either and it would work just fine. Again, these are details we'll get into in great detail when we're designing amplifiers. For right now, I just wanted to present some of this data. And again, another website that has a lot of good transformer information besides Hammond is EdCore. And if we look at their site for a second here, transformers, we can look at, classic tube audio. We have single-ended output, push-pull output, and power transformers, of course. But if we look at, say, single-ended output transformers for a second, we could just hover on one and it shows us its schematic and so on. So this is a good source for power transformers as well as Hammond. Now, before we leave these web pages, let's go on over again to the EdCore page. I like it because it has the prices listed. And as you can see, these single-ended output transformers tend to be pretty expensive, $152. We do have some less expensive ones down here, $42, $79, but generally they're pretty expensive. And if we go over and look at some of their power transformers, let's see what we've got for those ones. Well, we've got $118, $157, $138, $80. So again, these are very expensive as well, and that's the drawback to vacuum tube amplifiers and power supplies. We tend to use really expensive transformers, but that's the price we have to pay if these are the amplifiers that we want to build. So that's it for today's video. This wasn't meant to be a complete treatise on transformers. That's way beyond anything we're going to do, but hopefully it gives you just an idea of what we're going to be dealing with, and we'll delve into this in much more detail when we actually design and analyze amplifiers. So that's it for today, and I'll see you next time around.